Let's go back to my triangle. The point of the dihedral group is to look at all of the symmetries of the shape. We looked at the rotational symmetry, but that's not the only kind of symmetry that this shape has. I could draw a vertical line through the center or through the top vertex, and then we're going to flip across this line. When we do that, the 1 at the top stays where it is, and the 2 and the 3 flip. So this is a flip. I'll denote this particular flip by F1. And it's not the only flip I could do. I could flip through a line passing through any vertex. So this one, we want to flip across this line. We'll call this F2. When we do, my second vertex stays the same and the first and third flip. And then for the triangle, we have one more. We can flip through this line right here. We'll call this one F3. When we do, my 3 vertex stays where it is and the 1 and 2 flip. So if I consider my 3 rotations along with my 3 flips, I have all of the symmetries of the triangle. And this is called the dihedral group on the triangle. So we have lots of dihedral groups. The fact that this is a triangle tells me this is going to be denoted as D3 since the triangle has a 3-fold symmetry. So let's look at this group a little bit more. We previously talked about how the group of rotations, R0, R1, R2, which is a group, in fact it's a subgroup of this, can be generated by just R1. As a result, we tend to write R1 as just R, and R2 would be R squared, and it's common to denote the identity element as either an I or a 1. So I want to see if I can condense these F's a little more so I don't have to deal with so many subscripts. Let's denote F1 by F and see if I can find ways to write F2 and F3 with just these elements here. Let's look at RF. The first thing I need to do is to rotate 1/3 of the way clockwise. So F is a flip through the vertical line here, so 2 would stay at the top, and 1 and 3 would flip. So if I look back at my original triangle and labeling of these vertices versus these, we can see that that's the exact same thing as flipping along vertex 3. So this is the same thing as F3. What if we do R squared F? The first thing we need to do is rotate twice. When we do, the 1 moves to the bottom left, the 3 will move to the top, and then the 2 moves to the bottom right. We then need to perform my flip. And once again, F is the vertical line of symmetry here. So 3 would stay where it is, 2 would come over here, and then 1 would move to the bottom right. And so comparing this one to my original triangle, we can see that this is the same thing as F2. So with this, I can write my other 2 elements as RF and R squared F. So this is a group with 2 generators. We can generate it just by 1 rotation and 1 flip. Let's go back to the square and consider it as well. We had our rotation groups of R0, R1, R2, and R3. And in this case, we will also have 4 flips. We have the flip through the vertical line. We can flip through the horizontal line. Or we can flip through the diagonals, and there are 2 through the diagonals. So here would be my 4 groups. So we could call these F1, F2, F3, and F4. But it turns out that this group can also be generated by just R and F. In this case, we would have R squared and R cubed. And if I call the vertical line F, my 4 lines would be F, RF, R squared F, and R cubed F. And I'll leave it up to you to verify that and actually perform these 3 group operations, RF, R squared F, and R cubed F, and try to determine which one of these lines each one of these represents. And so this would be the dihedral group D4. And we can expand this idea. Whatever our degree of symmetry is, that tells me the subscript on the D. And D just stands for dihedral.